Let's solve this linear trig equation. Make sure we're providing the general solution. In other words, we need the answers and every coterminal angle since we're not restricting our domain. First things first, let's isolate that trig function. It's root 3 tan theta plus 1 equals 0. I think the first thing to do would be to subtract 1 from both sides. Root 3 tan theta equals negative 1. Now we'll isolate the trig term. This means tan theta equals minus 1 over square root of 3. We're looking for theta, so to undo the tangent, we take the tan inverse of both sides. This makes theta equal to tan inverse of minus 1 over root 3. Now to make our lives a little bit easier, we're just going to take the absolute value of this, make it positive, and then we can just check the unit circle in the first quadrant for the reference angle. We'll get the other solution by looking at the different quadrants and using the cast rule. 1 over square root of 3, if you look on the unit circle at pi over 6, we would see that cosine of pi over 6 is square root 3 over 2, sine of pi over 6 is 1/2. Knowing that tangent is sine over cosine, y over x, 1/2 over square root 3 over 2 would be our answer for tangent here, and those halves would cancel. What I'm trying to say is that tan inverse of this is going to be pi over 6. You could check this with a calculator as well. But here's where we need to be very careful. Originally, we had that tan theta is negative. And according to the cast rule, tangent is negative in the second and fourth quadrants. So we actually need the angle in the second quadrant and the angle in the fourth quadrant, where this angle is pi over 6 and this angle is pi over 6. Remember, halfway around the unit circle is pi, so the angles we want are actually pi less a pi over 6, and also we went around the circle once to make 2 pi less pi over 6. That would give us the angle in the fourth quadrant. Computing these very quickly, 6 pi over 6 minus 1 pi over 6, that's 5 pi's over 6. 12 pi's over 6 minus 1 pi over 6 is 11 pi's over 6. And these are both answers over one revolution of the unit circle. However, we weren't restricting our domain. We're looking for a general solution, so we need to also include every single coterminal angle. The way we do that is we add on plus 2 pi n to both of these. The 2 pi, that will give us coterminal angles, and here n is an integer. That will give us every single time around the unit circle, either way, clockwise or counterclockwise, that hits these angles. Thus, this is the full solution. It's a bit of a bear, and we had to know how to regularly solve linear trig equations and use the cast rule, think about some different angles, a whole bunch of things going on. I would definitely watch this video again.